Okay, so the empirical rule states that for any large population, in other words, if we measure the heights of a large population of students in a university, we can get all those heights and find a mean value, x bar, for the heights and a standard deviation value from that mean. And the empirical rule states that 68% of all those values, all those measurements, will lie within one standard deviation of the mean. And so the range that we derive from the empirical rule would be the mean minus one standard deviation, comma, the mean plus one standard deviation. Okay, 95% of all the values we record from the survey will lie within two standard deviations of the mean. So the range would be x minus two standard deviations, comma, x plus two standard deviations. And almost all of the values that we recorded, 99.7% of all the values or heights that we took, they would lie within three standard deviations of the mean. So those heights would always be somewhere within the mean minus 3 times the standard deviation up to the mean plus 3 times the standard deviation. So as we say here, so let's say we measured the heights of a large population of students in a university and found that they had a mean height, x bar, equal to 180 centimetres and a standard deviation from this at 10 centimetres. Okay, so if we were to plot this data using a histogram, we would plot frequency against height, okay, and we would get this kind of histogram, which would in fact give us a normal distribution. Okay, the data we would find for a large enough population would be normally distributed and not skewed positively or not skewed negatively, like we meant in the statistics chapter. And with respect to this data, the empirical rule is simply stating that 68% of the data, of the heights, will be in the range here. If we consider this to be the mean value, which was our 180 centimetres here, so that's our 180 centimetres here. These are the taller people going that way, and these are the smaller heights going that way. But 68% of all the recorded heights would be between 180 minus 10 centimetres, so it would be 170 there, up to 180 plus 10 centimetres, that would be up to 190 there. So 68% of all the data would be there. And actually, if I was to pull one piece of data out of the 1,000 pieces of data, the probability that the height would be between 170 centimetres and 190 centimetres would be 0.68. Okay, and the empirical rule states that 95% of the data will fall between the ranges of the mean, which is 180, minus 2 times the standard deviation, so this would be 160 here, up to the mean, which is 180, plus 2 times the standard deviation, up to 200 centimetres. So 95% of the heights recorded would actually lie within the range 160 centimetres to 200 centimetres. And almost all the data, or 99.7% of the data, those heights would all lie within the range 150 centimetres to 210 centimetres. Okay, and so basically just to recap there, if we were to take a piece of data out, the probability that that piece of data or that height would be within one standard deviation of the mean would be 0.68, or that height would be in the range of the mean plus or minus 2 standard deviations is 0.95, or the probability that any height I took out would be in the range the mean plus or minus 3 standard deviations would be 0.997. So the best way to look at these is by example. So the mean of the mean x bar of a distribution is 54 and the standard deviation is 3. Find the range x bar minus 1 standard deviation, comma, x bar plus 1 standard deviation, and then go on to find the range within which 95% of the data lies. And then finally, if a value is selected at random from the distribution, find the probability that it is in the range x bar minus 1 standard deviation, x bar plus 1 standard deviation. So to solve this, we simply say that the x bar, the mean, equals 54, standard deviation equals 3. Our range looks like this, x bar plus or minus 1 standard deviation. That gives us 54 minus 3, comma, 54 plus 3, that's 51, comma, 57. That's the range. 95% of the data lies within 2 standard deviations of the mean. So if we were to calculate that, we now have 54 minus 6, 54 plus 6. That's within the range 48, comma, to 60. And the probability that a value is in the range x bar minus 1 standard deviation, x bar plus 1 standard deviation is 0.68, as 68% of the data will lie within this range according to the empirical rule. Okay, second example. Let's make it a little bit bigger. Okay. The weights of a group of 1,000 children were normally distributed with the mean x bar equals 42 kilograms and a standard deviation of whatever it is. We don't know what that is yet. 950 of the children were in the range 30 kilograms to 54 kilograms. First, express 950 as a percentage of 1,000. Then complete the statement here. Then use the information given to find the value of the standard deviation. And finally, if a child is selected at random, find the probability that the child's weight is in the range 30 kilograms to 54 kilograms. Well, first of all, to express 950 as a percentage of 1,000, we simply put 950 over 1,000 times 100. That's 95%. And we should know or recall from the empirical rule that 95% of children lie in the range. Because it's 95%, it's the mean plus or minus 2 standard deviations. The third part then is we're going to use the information given to find the value of the standard deviation. Well, 950 children are in the range 30 to 54 kilograms, and this represents 95% of the data. Okay, and 95% of the data range is, we can find that normally by equating x bar, the mean, minus 2 standard deviations, or x bar plus 2 standard deviations. So we'll just go with this one here, and we can say that 30 must be equal to the mean minus 2 standard deviations. Okay, so if we bring our 30 over here, we'll have 42 minus 30, and bring our minus 2 standard deviations over here is equal to 2 standard deviations. 42 minus 30 is 12. That's equal to 2 standard deviations, so our standard deviation is equal to 6. Now we could have done the same here by equating 54 equal to x bar plus 2 standard deviations. And that would give us 54 is equal to 42 plus 2 standard deviations. 54 minus 42 is equal to 2 standard deviations. 12 is equal to 2 standard deviations. So 1 standard deviation is equal to 6, which is the same answer because it's the same standard deviation. And finally, if a child is selected at random, find the probability that the child's weight is in this range, 30 to 54. And we've already seen that that's associated with the 95% range. So the probability that the child's weight is in that range must be 0.95. So let's look at some terminology here. So we can gain information about the whole population by surveying a smaller part of the whole population known as the sample. Okay, and this notion of a confidence interval, the confidence interval is given by this formula here, p hat minus 1 over square root of n. Our population proportion is greater than that, but it's less than p hat plus 1 over the square root of n. Okay, so our 1 over root n, that's known as our margin of error E, and that's equal to 1 over root n, where n is the sample size. And p hat itself, we can always calculate that because that's the number of whatever people were doing or saying whenever, over the total number of people who were asked, what they preferred or what they didn't like or whatever. By example, it becomes clearer anyway, okay? And p hat is otherwise known as the sample proportion, and basically it's an estimator of the population proportion, which is kind of not generally known, okay? So, and also to say, that, our 95, if this is the confidence interval in the formula for us, for our course, we will kind of also know this as the 95% confidence interval, and sometimes it's also known as the 5% level of significance, okay? So our 95% confidence interval we'll calculate it using this always, or they might call it the 5% level of significance. But what does it mean? Okay, when we calculate this value for our sample in a minute by example, we can confidently say that if we surveyed many samples on the same day, that we would get the same results in 95% of these samples. So let's look at a real example, okay? So here, a random sample of 400 people are given a flu vaccine. 136 of them experience discomfort. Find the 95% confidence interval, or the 5% level of significance. How do we do these? Well, we always, first of all, look for our sample size, which is n. We work out our margin of error, which is 1 over root n, is 0.05. Then we calculate p hat, and p hat in this instance, a random sample of 400 people are given a vaccine. 136 of them experience discomfort. So p hat is that proportion, the sample proportion who experience the discomfort. So it's 136 over 400 is 0.34. So that means that our 95% confidence interval, if we're trying to work out where the population proportion sits, well, it's greater than this value here, but it's going to be less than that value there. So we have p hat is 0.34 minus the margin of error, and p hat plus the margin of error. So that's 0.29 to 0.39. This is our 95% confidence interval. It's 0.29 to 0.39. And if this was the case, if the newspapers found out that people got the flu vaccine and they suffered, they had discomfort, they might hear about this and do this survey just to see how many people are suffering, but it won't really print the numbers as such in the headlines. It would just say 34% of flu patients feel the pain, and in small print underneath, the margin of error is 5%, which is from here. Our 34 is from down here, and our 5% is there. Okay? So we look at a second example, which is question 13 in the extra chapter. The results of a survey showed that 360 out of 1,000 families regularly purchase the daily bulletin newspaper. Construct a confidence interval, 95% or 5% level of significance, doesn't say it here, but it will in an exam, for the proportion of families who purchase the daily bulletin. Okay, first thing, sample size is 1,000, margin error is 1 over the square root of that, so our margin of error is 0.03. Our sample proportion, p hat, is equal to 360 divided by all the people who were asked. How many said they did out of how many were asked? Okay, so that's 0.36. Okay, and so this would mean then that our population proportion would lie within 0.36 minus the margin of error up to 0.36 plus the margin of error. That works out at 0.33 to 0.39. So our 95% confidence interval is 0.33 to 0.39. So in other words, the papers would say 36% of families buy the bulletin, margin of error is 3%. So here is our 3% margin of error here. Here's our 36% of the people. Now, if we were to go on now and look at hypothesis testing, well, hypothesis testing is the type of statement that the paper will make or companies will make based on a survey. or they'll make a statement, and we'll do a survey to see if they're telling the truth or not, or if we can accept or reject their statement. So if a newspaper makes a statement like 36% of families buy the bulletin, then we call this statement our null hypothesis, and that's known as H subscript 0. Now, we can check to see if that's true or not, and we'll accept or reject the null hypothesis. But before we do that, we set up a kind of opposite statement to this null hypothesis. This is known as the alternative hypothesis, H1, H subscript 1. And, the alternative hypothesis would be 36% of families do not buy the bulletin. Okay, so it's the direct opposite. And I always just like to use the phrase do not to whatever hypothesis they give me. Whatever the null hypothesis is, the alternative one is the same sentence really, but we just put in do not. Okay. So let's think about testing a null hypothesis to see if we can will accept or reject it. Okay. So here's an example. The bulletin says that 36% of families buy it. 2,000 families were surveyed, and 740 said they bought the bulletin. At a 95% confidence interval, or that 5% level of significance, do or would you accept the bulletin's claim? Okay, well, we set up the null hypothesis first, which is 36% of the families buy the bulletin. The alternative hypothesis is 36% of families do not buy the bulletin. So we can look at this by, first of all, working out, we should really work out our margin of error first always, because n is equal to 2,000. So our margin of error is 0.022. We can then look at our p hat. Okay, bear with me. We can look at p hat then, the sample proportion, with 740 people out of the 2,000 who were asked. That's p hat is equal to 0.37. So our 95% confidence interval will always be p hat minus the margin of error to p hat plus the margin of error. So that's 0.348 up to 0.392. So we round them off to 2 decimal places. That's our population proportion sits in between 0.35 and 0.39. So our 95% confidence interval looks like this. Now, to see if we accept or reject the null hypothesis, they're saying that 36%, that's the same as 0.36. So we look at our range, goes from 0.35 to 0.39, and yes, 0.36 does sit in within the range, or lie within the range. We have 0.35 up to 0.39. 0.36 sits in between those. So we will, because it's within the interval, we will accept the null hypothesis. It looks like 36% of families do actually buy the bulletin. Okay, let's just look at 2 examples which ask what sample size n would be required to have a margin of error E equal to, say, in the first instance, 0.05. Well, the first thing to do is to equate 1 over the square root of n equal to 0.05. We need to get rid of this square root sign here, so we square both sides. So we have 1 over the square root of n times 1 over the square root of n, and that gives us 1 over n. And 0.05 squared is 0.05 squared. And so now, if 1 over n is equal to 0.05 squared, algebraically what we can do is we can multiply both sides by n to lose the n here. So we have n here and n here. They'll cancel. And then we can divide both sides by 0.05 squared here. So we'll end up with, they'll cancel, of n is equal to 1 over 0.05 squared. N is equal to 400. And we're doing the same thing on this side. If our margin of error is 2.5%, that's the same as 2.5%, which is the same as 2.5 divided by 100 is 0.025. So now we equate 1 over the square root of n equal to 0.025. And again, algebraically, the first thing we need to do is square both sides. So 1 over root n, 1 over square root of n squared is actually 1 over root n, and this is 0.025 squared. So then we'll multiply both sides by n. They'll cancel, so we've 1 is equal to n by 0.25 squared. So now we'll divide both sides by that, 0.025 squared. 0.025 squared will go there. They'll cancel, so we'll have in fact that n is equal to 1 over 0.025 squared. N is equal to 1600.